Assalamualaikum and hello everyone. My name is Nazhif bin Amzan, and today I want to explain about my answer for assignment 2, computer architecture organization. And today I will start with the question 1. It about Hamming code error detection and correction. And for question 1, it involves a 12-bit Hamming coded word that was retrieved from a memory. The bit sequence retrieved is 1011100111, and this word consists of 8 data bits and 4 parity bits. And based on what I learned in topic 5, the Hamming code is used to detect and correct single bit errors in a memory by using a check bit placed at the position that are power of 2, that is position 1, 2, 4 and 8. For part A, showing the single bit error. Okay, first I map each bit to its position from 1 to 12. Then where the parity bits are at position 1, 2, 4 and 8, and the data bits D1 through D8 fill the remaining position. And to find the error, I perform 4 parity checks using XOR operation. Okay, check C1 will cover position 1, 3, 5, 7, 8, 9. Okay, my bad, 1, 3, 5, 7, 9 and 11. I XOR does bit and got a result of 1, which means C1 is failed. And check C2 cover position 2, 3, 6, 7 and 10 at 6, 7, 10 and 11, and I XOR, the result is 0, so C2 is pass. And then for C4 covers position 4, 5, 6, 7 and 12, XOR result is 1, so C4 is fails. And check for C8 covers position 8, 9, 10, 11 and 12, and XOR result is 1, so C8 is fails. And then for part B, position of the erroneous bit. So syndrome word is formed by combining C8, C4, C2 and C1 in that order. So my syndrome is 1101, which in binary is 1101, and in decimal that equals to position 6 in data bit 3. So and then you know the bit position, so the bit that we receive as 1, but the correct value for position 6 is 0. So for part C, original 8-bit data message. After correcting position by position 6 by flipping the bit from 1 to 0, I extract the 8 data bit from position 3, 5, 6, 7, 9, 10, 11 and 12 of the correct word. So the original 8-bit data message is 1001101. So my reflection for question 1 is a bit hard, where I found the challenge here was setting up the bit position, and do the table correctly and making sure that I assign the right position to the right parity and data bit. So I learned that the key to Hamming code is that parity bit always a power of 2 position, and the syndrome value directly tells you which position has the error, which is very elegant. For question 2. For question 2, ask me to multiply x equals 15 by y equals -4 using a 5-bit word and Booth's algorithm. So part A, 5-bit representation. So first I convert both value to 5-bit 2 complement. Multiplication m equals to -15. In binary, positive 15 is 0, 1, 1, 1, 1. and I flip and add 1 to get 1001. And then multiplier Q equals to -4. So positive 4 is 0, 0, 1, 0, 0. And flip and add the 1 and give 1, 1, 1, 0, 0. For part B, boot algorithm tables. Okay. For boot algorithm use 4 register, A the accumulator, Q the multiplier, and Q minus the extra bit, and M is multiplier. We also need a negative M, which is 0, 1, 1, 1, 1. So the rule is, if Q 0 and Q minus are 0 or 1, no operation, just shift and right. And if Q 0 and Q minus are 1, 0, perform equals minus M. If Q 0 and Q minus 1 are 0, 1, perform equals plus M. So then we arithmetic shift right the table combine, and A and Q register by 1 bit. So for the cycle, for first initial value, A is 0, 0, 0, 0, 0, and Q is 1, 1, 1, 0, 0. So Q minus 1 is 0. And then for cycle 1, first cycle, Q0 is 0 and Q minus is 0, that 0, 0, so no operation. Shift right, stay 0, 0, 0, 0, 0, and Q becomes 0, 1, 1, 1, 0. For cycle 2, Q0 is 0 and Q minus is 0, again 0, 0, no operation. Shift right and stay 0, 0, 0, 0, 0, and Q becomes Q0, 0, 1, 1, 1. For cycle 3, Q0 is 1, so Q minus is 0, that 1, 0, so A equals to A minus M. So A equals to 0, 0, 0, 0, 0 plus negative M, which is 0, 0, 0, 0, 0, and plus 0, 1, 1, 1, 1, giving 0, 1, 1, 1. Then shift right, A becomes 0, 1, 1, 1, Q becomes 1, 0, 0, 1, 1, Q minus becomes 1. And for cycle 4, Q0 is 1, so Q minus is 1. That's 1, 1, operation, shift. So we shift it right. And A becomes 0, 0, 0, 1, 1, and Q becomes 1, 1, 0, 0, 1. And Q minus the 1. And then cycle 5, Q0 is 1 and Q minus is 1 again. So 1, 1, so no operation. So we shift it right and becomes 0, 0, 0, 0, 1, and Q becomes 1, 1, 1, 0, 0, and Q minus stays 1. And then the final result is AQ concatenate. So for the answer is 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, and binary, which equal to positive 60. So in the logic here, where negative 15 times negative 4, so our answer will be positive. So the sign bit is 0, so our answer is verified correct. And then for reflection on question 2, the most challenging part is remembering the correct rule, where when Q0 and Q minus is 1, 0, it's mean what? So it's mean subtract. And if 0, 1, it means what? Means addition. So that's what that most challenging part for boot algorithm. And then for question 3, the storing division algorithm. So this for this question, as divide A equals 7 by B equals to negative 5 using a 4-bit word and restoring division algorithm. And then from my lecture note, I also do a research where for the restoring division algorithm, it's work on the magnitude of number. So the sign is handled separately at the end. So dividend D equals to positive 7. So I set equals 0, 0, 0, 0, and Q equals to 0, 1, 1, 1. So the divisor magnitude M equals to 5, which is 4 bit, is 0101. So negative m, the 2's complement is 1011. So the algorithm has 4 cycles. For a 4-bit word, each cycle does 3 things. So first one is it shift to combine A and Q. This is the left by 1, and then subtract M from A, and then check the MSB. MSB 0 or 1, so non-negative or negative. And then for cycle 1, shift left. A becomes 0001 and Q becomes 110. And then we put the question mark in the back, and then subtract M. A equals to 0001 plus 10011 and equals to 1100. MSB is 1, negative. So restore A equals to 1, 100 plus 0, 101 equals to 001. So Q 0 equals to 0, and state A equals to 001, 0001, and Q equals to 1100. Then for cycle 2, just shift left. Every cycle we just shift. So don't forget to shift left and becomes 0011, and Q becomes 100 question mark. And then a question mark here means you can put question mark or you can put 0. But at the end, for sign bit, we need to refer the MSB. If MSB is 1, negative, we put 0, and 0, we put 1. And then for restore, A equals to 1110 plus 0101 equals to 0011. So set the Q 0 equals to 0. State A equals 0011 and Q equals to 1000. Then for the, I think this is the last cycle, shift left. A becomes 011 and Q becomes 000 question mark. Subtract MA equals to 0111 plus 10011 and equals to 10010. That is 5 bits, so we take a 4 bit only. And then our answer is 0010. And the carry out means the result is non-negative. So our MSB is 0, keep A equals 0010, so Q 0 equals to 1. State equal 0010, Q equals to 0001. And then our answer is, for the remainder is 0010 equals to 2, and our quotient is 0001 equals to 1. We simplify 7 equals to 5 times 1 plus 2. And then for reflection, for question 3, the most challenging part was the sign handling. So I had to remember that we divide using the method and only apply the sign rule at the very end. And also find it's very tricky when you want to keep track on shifting or subtract. Then you need to make it without any mistake, without any arithmetic mistake. And then for question 4 involves a 16-bit instruction format. With a lot instruction, the opcode is 0x12, which means hex 12, or we can say 12 hex. So the register field specifies R4 and the address field is 0x3c. And then from figure 1, you can see the register and memory values. And R2 equals to 28, and R4 equals to 40, and R5 equals to 3c. And memory at 1A equals to 3F, at 2B equals to 5C, and 3C equals to 8E, at 4D equals to A1. So based on topic 10 that we already go through it, so For part A, immediate addressing. In immediate addressing, the operand is the value in the address field itself. So no memory access is needed. So the operand equals to 3C directly from the instruction. And for part B, direct addressing. In direct addressing, the address field gives the memory address where the operand is stored. So the effective address EA equals the address field, which is 3C. And I look up the memory at 3C, which equals to 8E. The operand is 8E. So for part C, then register indirect addressing. In register indirect addressing, the register R4 hold the effective address. So EA equals to content of R4, which is 4D. So I look up at the memory 4D, which equals to A1. Then the operand is A1. In indirect addressing, there are two memory lookups. For part D, indirect addressing, so there are two memory lookups. So the first one is the address field is 3C points to a memory location whose content is another address. So for memory, 3C equals to 8E. So this is the effective address. Then I need the memory of 8E. However, 8E is not listed in the figure 1, so the operand is not available. So the answer for part D is not available for address of 8E. So then from this question, what I learned in question 4, from this question I learned how different addressing modes affect how many memory access are needed. And immediate is the fastest with no extra memory access. Indirect is the slowest because it requires 2 memory access. So this is so important for processor performance design. So then for closing, I would like to share again my reflection for this assignment 2. For question 1, I use code parity to check find single bit error at position 6 and recover the original 8 bit. So in question 2, I applied a boot algorithm to multiply -15 by -4 and got positive 60. In question 3, I used restoring division to divide 7 by -5 and I get a quotient -1 with remainder positive 2. And then in the question 4, I explain for addressing mode and determine the operand value for each address. And I think that's it. So thank you for watching and Assalamualaikum.